Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson, we did talk about Lenz's law. We said Lenz's law, or basically Lenz's law, talks about the direction of the electrical, or the direction of the electrical current that flows through the, let's say, through the circuit, or through the coil that we were talking about. So we said basically the direction of the current will be, or the magnitude, or the direction of the magnetic field of the current induced will be in a direction opposite to the change that created it. And of course we said when we are normally, that is what we went through, if we bring or insert the north pole of the magnet into the coil, of course there will be an electromotive force inducing the coil, but the direction of the current in the coil will be, of course, there will be a current in the coil. This current will produce its own magnetic field. The magnetic field of the induced current will be opposite to the magnetic field of, let's say, the bar magnet. And of course, these two will oppose one another once the magnet is being inserted into the coil or the solenoid, let's say. But if the magnet is, and of course, the direction of the magnetic field would be opposite to one another. That is when we bring them close to one another. But what happens when we pull the magnet out of the coil, let's say, or the solenoid? Of course, in this case, let's say the two forces, or you can say the magnetic field lines, will be in the same direction, and of course they will once again oppose one another. But this time, like in the first place, they were repelling one another, but the second time, once the magnet or the coil is, let's say, move away from one another or relative to one another, then of course these two will attract one another, and the direction of the magnetic field in this case will be in the same direction. Okay, that was basically Lenz's law, and of course we ended up right at this point. So we're going to talk about the right-hand rule can be used to determine the direction of the induced current. That is, we're still talking about Lenz's law, okay? But in order to find the direction of the current using Lenz's law, of course, we need to use the right-hand rule for that. Okay, so here's what we're going to do. Normally, you've learned how to use the right-hand rule, yes? Chapter 5, don't forget. Okay, and then of course we're going to use the same thing here, but this time, like in chapter 5, we had the direction of the electrical current. We were, let's say, aligning or curling our finger in the direction of the current, and of course our thumb were pointing north, let's say. This time we're going to do the opposite. We basically know which end of the coil or the solenoid is north or south, and then based on that, let's say the north first. We know which end is north. We point our thumb into that direction, of course. We're going to use the front of the coil mostly, all right, just for simplicity. And then the direction of curling our fingers would indicate the direction of the current. All right, now let's dive more into this. Okay, so take a look at this one here, for example. That is basically we are inserting a permanent magnet, or let's say a magnet into a solenoid, as you can see here. But this side of you can see here, this side of the magnet is basically north pole, and based on Lenz's law, once we are inserting this magnet into the coil, of course, this side of the coil or the solenoid is going to be north as well. So we have north and north. These two are going to oppose one another. So if you know which end of the solenoid is north, then of course the rest will be very easy, or finding the direction of the current is going to be very easy. And how do we know that? All right, just take a look here. So if this is north here, so we're going to align our finger. Your thumb must point to the direction of north here. So in this case, of course, take a look what would be the direction of the current. So my fingers are pointing upward. In another word, the direction of the current must be pointing upward. But take a look at the direction of the current that you see here, yes? So if that is the case, so here's what we're going to do, yeah? If that is the case, you can follow all this, right? So in this case, we can say the direction of the current is this way, but remember this one is going to, let's say, to back of the coil, and then of course coming back this way, or you can say the direction of the coil is this way. If not, just follow this one here. So this is upward. So if we keep following that one, of course, we can say it is from the left to the right. That is when we insert the coil insert the magnet into the coil or the solenoid here. All right, what happens when we pull the magnet out of the coil, let's say? So we know that once again, using Lenz's law, if this is the north pole and if these magnets are being removed or moved away from the coil, of course, now this is going to be south this time, because now once again they are opposing, let's say, or the magnet of this, the magnetic field of this coil or solenoid is going to oppose the magnetic field line of this magnet here, so that it doesn't allow it to, or doesn't let it to move away, or it doesn't allow let's say, the total magnetic field of this to change, yeah? So in another, like simply, this is just going to be south. If that is the case, then the other end is going to be north. If that is the case, once again, so you have to align your hand in a way such that your thumb points north. If I do this, that is south, so I'll have to do this way, yeah? But if I'm drawing this way here, now obviously you can see here, this would be the front of the coil here. Or if I do it this way or something better, I'll have to adjust my hand or go to the other side. So this is north, yeah? In another word, you can see here, my fingers are pointing downward. Once again, always use the front of the coil so that you have an idea which direction the current is moving. So in this case here, if this is north, if you can see here, okay, so the direction of the current must be downward through this solenoid here. Let's say this is the direction of the current. So if you're following this one, of course, you can see here, the direction of the current is moving this way. In another word, you can say, or we can say the direction of the coil is from right to left this time. If not, you can take a look at these. Of course, these drawings will also help you to determine how you can find the direction of the current. So you've learned about this before, so I hope these are clear enough, because I don't want to explain this one furthermore, because I believe this is easy enough for you guys to do them. All right, now we have another question which is also very important. I want you to take a look at this one right here, because there is an idea in this. Okay, it says what? An electromagnet is placed next to a coil of wire in the electromagnet shown below here. So this is what you see here. We have an electromagnet, and of course there is a coil you can see. This coil you can see is connected to a resistance here, or a resistor. Connect to this, a load. It could be a light bulb or whatever. We don't need this the detail here. Okay, so it says according to Lenz's law, what will be the direction of the induced current in the resistor R, in this resistor? What will be the direction of this, the current in this resistor, are in the following cases. So the first case is if the magnetic field suddenly decreases after the switch is opened here. Now, before talking about this one, I would like to give you an information about this one here. So remember, this electromagnet, it behaves just like a permanent magnet. But if that is the case, how can we do this one here? So let me give you a little bit of information or how we can do this one. Let's, for a second, let's just ignore this one and then see how it happens. All right, so take a look here. Imagine we only have this electromagnet. Why am I doing this? There's a reason for that, yeah? Because I need to know which side of this is north and which side is south, and then I can use this one or consider this as a permanent magnet, and then of course using this magnet I can tell the direction of the current in the other coil here. So how can I do this? Now of course chapter 5 we've learned that when current passes or flows through a coil, let's say, and of course we're going to align our finger in the direction of the current, then of course your thumb would normally or automatically would be pointing north. So remember this is the north, or you can say the, this one here. So this is basically, you can say the positive, or this would be the direction of the current here, because current is in the direction of the positive charge. So this is basically the direction of the current here. If that is the direction of the current, watch this, yeah? Remember, this wire is going beneath, or you can say behind the coil, and of course it's coming backward here, you can say, yeah? So of course, if I do something like this, or if this is the coil here, so it's going to move like this one here. So if I, for example, align my hand here right in front of the coil, you can see this would be the direction of the current here. It goes all the way behind the coil, you can say, or this, and then of course it comes back like this. So this is going to be the direction of what? The direction of the electrical current. Now, if that is the direction of the electrical current, if I do this one here, so I do know that this side is going to be north, correct? Yes. If that is north, then of course the other side is going to be south, and of course now it is, the next part is easy enough. Okay, so once again, the first part, we're going to use the electromagnet or the direction of the current. That is chapter 5, by the way. We're going to see which side is north, which side is south. That is the main, you can say the first step in here, yeah? Second, it says the magnetic field suddenly decreases after switching or after the switch is open. So this is the same as if, let's say, if I move the whole thing, let's say, now we can, of course, bring back the coil. All right, so take a look here. Remember, that was north, okay? And then this is south. In another way, you can also tell, if you were not sure, like if this is not given, you can always use the direction of the magnetic field line here to tell the direction as well. So we do know that if this is the direction of the magnetic field, we know that the direction of the magnetic field always goes from north to south. In another word, if this is going to be something like this, yeah, or this side here indicates that this is going to be north, and then the other side is going to be south. That is another way to tell which side is which. Now, after we know this one here, I'll do something different here to help you understand this better here. So let's hide this one a little bit. All right, so what does it say? It says this magnetic field line is going to, or it is decreasing. What does it say? The magnetic field is suddenly decreases after the switch is open. This is the same as if we have a bar magnet. Let's say this is the north side, and this is the south side of these were the poles here. And we are going to pull this magnet away from the coil. If that is the case, watch this, guys, yeah? So if this is north, yeah? So imagine this, there's a magnetic field line. Imagine this is, by the way, this magnetic field line comes from the coil, but since this coil behaves as a permanent or something like a permanent magnet, in order for you to understand easier, I've just replaced that one with a permanent magnet because it would be easier to understand this. So when you turn the switch off, basically the magnetic field line are decreasing suddenly, or let's say the decrease is more and more. It's almost like you are moving this permanent magnet away from this coil. But if this side is north and you're moving this magnet away, what do you think this pole of this coil is going to be? There is a change in the magnetic field, so of course there is a current induced. This current induces its own magnetic field. These two will oppose one another. If this is north, this is going to be south. And if this is south, the other side is going to be north. If this is north, now we have north and south. Can you tell the direction of the current that is induced, let's say here? Of course you should be, yeah? So once again, all right, just make sure that your hand would align, or your thumb points north, and then your finger, or curling your finger, would represent the direction of the current here. So in this case, the current is moving downward here. So if I follow this one here, you can see that we can say the current is moving from left to what? From left to right. That is for the first part. It says the magnetic field is suddenly decreasing. It is almost like as if you are moving this bar magnet away from the coil here. So this is going to be the direction of the current through the resistor, which is going to be from left to right. Now we can go back and explain this one more time. We said this is going to be north and this is going to be south, and here is the magnetic field lines right here. Okay, so remember this. Now, as you are, or when you are opening the switch, this magnetic field lines are decreasing. If these magnetic field lines are decreasing, it is the same as if, let's say you are moving, or this behaves like a bar magnet, it is the same as if you are moving this away. Because take a look at these magnetic field lines here. This is going to decrease something like this one here, yeah? If it is decreasing, that means this magnetic field line, or behaves as if this, let's say, coil is being removed or moved away from this coil. So that is what happened in the first place. All right, what about the second one? It says the coil is moved closer to the electromagnet. Now, let's talk about this one once again. We said this is the north, okay, and this is the south. This time says the coil is moved closer to the electromagnet. If it is moved closer, and of course we do know that using Lenz's law, if this one brought closer to this, of course this two, there will be an induced current here. This induced current will produce its own magnetic field. These two will oppose one another. So this side is also going to be north as well. This is going to be south. Because these two, of course, now are going to oppose one another using Lenz's law. So if that is the case, what is the direction of the current through the resistor? All right, so once again, use your right hand rule, yeah? So once again, my thumb is basically pointing towards the north, so the direction of the current is upward. So you can see here, this is upward. So upward here, that means in another word, it is going from right to left this time, and that is basically how it is. Okay, and you can see here, it is explained. I hope it is clear enough for you guys. Okay, take a look here. These are some national, or you can say Wazadi question. Says a bar magnet is positioned, so this is easy enough, near the coil of wire shown in the figure. What is the direction of the current in the resistor when the magnet is moved to the left? Remember, the magnet is moved to the left. Instead of telling you the magnet is inserted into the coil, they're telling you the magnet is moved to the left, and you can see this direction as well. So if this is south and it's moved this way, of course it's going to be south, this is going to be north. If that is the case, align your finger like this, it is going to be this way. So it is going to be this way here, so you can say it is moving from the right side to the left, of course, and that will be the direction here. So from the right to the left, which one is it? And that is going to be B in this case. All right, another example or another question, you can see that these two are very similar to what I have just explained. So you try them and get the answer correct. All right, now let's talk about another concept here. Now, so far we've been talking about the direction of the electrical current, and of course that was by using Lenz's law. So Lenz's law tells us the direction of the current that is flowing through the coil, through the solenoid, let's say. But what about the magnitude of or the value of the electromotive force that is induced here? Okay, because we haven't talked about this one, let's say, much, because we were just talking about the direction of the current. So in order to find the direction of the in order to find the magnitude, not the direction, in order to find the magnitude of the electromotive force that is induced using this electromagnetic induction, we're going to use Faraday's law, or Faraday's law of electromagnetic induction, you can say. So Faraday had an equation, of course, or using the Faraday's equation, we can tell the magnitude of the electromotive force that is induced through the process. Okay, so what is the Faraday's law of electromagnetic induction? Yeah, or what does it state? Faraday, of course, states that the electromotive force, the potential difference, the voltage, you can say, that is induced in a closed circuit is directly proportional to the rate of change of the magnetic flux through that coil here. So once again, and listen to what I say, Faraday said that the electromotive force, the voltage, the potential difference that is induced in a circuit, it is directly proportional to the rate of change of magnetic flux. When we say the rate of change, that means something divided by time, yeah? Or time change, let's say. And of course, the rate of, or you can say the rate of the magnetic flux. So can I say the electromotive force is basically induced is directly proportional to magnetic flux or change in the magnetic flux, because it says the rate of change of, so change of magnetic flux, of course, divided by delta time, you can say. And that is, of course, the what Faraday stated, and of course is one of the most important laws that we have. So basically that is what he said. He said the electromotive force, this symbol represents the electromotive force, or you can say the voltage, the potential difference if you rather to call it, but that is basically the electromotive force, okay? So the electromotive force that is induced or generated is basically directly proportional to the rate of change of the magnetic flux, yeah? Then of course this end represents the number of turns, you can say, because sometimes if we have a coil, let's say, or solenoid, we could have more than one turn here. And of course you might wonder, what about this negative sign? Remember that this or you can say this electromotive force that is induced, of course, it induces a current, you can say. This current induces a magnetic field, yeah? So this magnetic field that is induced, of course, is going to oppose the change of the magnetic field that created that one. So this negative sign represents that one here. But we've also learned that in chapter 5 that this magnetic flux, okay, equals to what? Equals to AB cosine theta, yeah? So by substituting this, of course, into the equation, we can get electromotive force equal to the minus or this negative number of turns that is going to be let's say area, that is cross-sectional area, that is the magnetic field, of course, cosine theta divided by delta t here. Now let me tell you something about the Faraday's law of electromagnetic induction here. So of course here's the equation. Electromotive force induced equal to negative N, that is AB here, we can say, or let's before that, let's start with the change of the magnetic flux, we can say, right, divided by delta time here. So we can see that the electromotive force is measured in volt, and of course the magnetic flux is measured in Weber. We've learned that, and of course this is second as well. So we can also say that the volt equal to what? Equal to, or before that, we can say, if we use cross multiplication, we can say Weber magnetic flux is basically equal to what? Equal to voltage times revolt times second as well. This is another important unit. You need to remember that. Now, you will see that in equations, we're going to use this one in two different ways. And one of the way is this, okay? So let's say the first way, we can have, remember, the magnetic flux is basically, we're going to substitute the equation of magnetic flux into this here. So we can say the electromotive force equal to negative N. We can use AB cosine theta, okay? And of course, divided by delta time. That is one of the equations that we can use. But remember this, when we are using this, there are two things that can change, yeah? And of course, we can either change, let's say, the cross-sectional area. That is unlikely, let's say, for most of the question, except in one of them. And of course, mostly the magnetic field is going to change. So how are we going to use this one? Because either change of these, of course, is going to induce an electromotive force for us. Basically, that is Faraday's law. So in order to focus on this one more here, we can say this equation, sometimes the area is going to change, sometimes the magnetic field is going to change. So of course, we're going to rewrite this one. Or instead of doing this one, I'll say, we'll say if the magnetic field is changing, or we can say the strength of the magnetic field, if B is changing, if B changes, yeah, we can rewrite the equation like this, electromotive force equal to negative N. We can use, of course, A cosine theta, and of course, we can say delta B here, divided by delta time. And of course, you do know that delta B here, of course, equals to B2 minus B1. That is what we're going to use right here in the equation. What if area changes here? Because sometimes area can change. Yeah? If area or cross-sectional area change, right, or changes, let's say, and then of course we can say electromotive force that is induced equal to negative again, that is N multiplied by B cosine theta this time, and then multiplied by, let's say, delta, change in area divided by delta T. But once again, change in area equal to area 2 minus area 1. And of course, you can find this one here, and then you can divide it by delta time right here. Oops, sorry for that. Okay, this would be the basically main equation that we're going to use, yeah? That is the main equation. It is either the area or the magnetic field is, strength of the magnetic field is going to change, or the area is going to change. If that is the case, you can use this equation. If not, you're going to go with this equation. Of course, we're going to use this equation only in one equation, but of course, don't be surprised if you are going to use this one in another situation too. Okay, now let's go back to the main equation here. Basically, these are what they are measured in. You can see that this is electromotive force measured in volt. That is number of turn. You can see B is magnetic field measured in Tesla. Magnetic flux is measured in Weber, or you can say Tesla meter squared. And of course, we have the rate of change of magnetic flux that is going to be Weber per second. And of course, we have delta T or T, which is measured in second here. Okay, now we have a few study tips before we move on, yeah? It says the negative sign indicates that the induced magnetic field, remember this, yeah? This negative, still we can say something belongs to the Lenz's law, okay? So the negative sign indicates that the induced magnetic field, this magnetic field that is induced, of course, it is going to be what? It is going to be opposing the change in the applied field. Remember, not the applied field, the change in the applied field, yeah? As stated by Lenz's law here. The term B cosine theta represents the component of the, let's say, of the magnetic field that is perpendicular to the plane of the loop. Because let me tell you what exactly this part means here. Because we've learned, or we've mentioned this one before, let's say, this is the plane of the area here. And of course, let's say this arrow here is basically the direction of the area, or perpendicular to the plane of the area. If the magnetic field is, let's say, so let me erase this one for now. If this is the, let's say, the magnetic field, all right, you can see that this is not perpendicular. This is at an angle to this one right here. So here's what we're going to do. If that is the case, you can see we're going to analyze this one to two components. And of course, we have perpendicular and of course horizontal component. We know that this is, the angle is basically has to be with the perpendicular one, because this component is going to induce, let's say, induce a electromotive force here, not this one, because this is going to be perpendicular to the plane of the area, or you can say parallel. By the way, this is the plane of the area. This is basically the direction of the area. So this component is going to be parallel to the direction of the area. Don't forget, because naming these could be a little bit confusing. When we say this is, for example, this is the plane of the area, that is normally, and this is perpendicular to that plane of the area. So, or you can say, if another word or another way to say that, we can say, if this is the direction of the area here, okay, and of course this magnetic field, these two are basically parallel to one another, which are both perpendicular to the surface of this this area, whatever you call it, yeah? Okay, so of course we call it the plane of the area here. So this, because the angle is basically with the perpendicular, with the vertical here, so this component is going to be b cosine theta here, and of course this side is going to be b sine theta. But like I said, this component is going to induce no electromotive force, because this two are, you can see that this component is perpendicular. It's a little bit hard to, I hope it doesn't confuse you, because this component, it is parallel to the plane of the area or perpendicular to the direction of the area, don't forget. Okay, so basically here's the direction of the area, so this is basically perpendicular. You can see the direction of this two. This is the plane of the area, perhaps not this one. Let me just so that stay with me for a second. Okay, I hope it doesn't confuse you. This is basically the plane of the area. This is perpendicular or normal to the area here. You can call it the direction of the area for now. And then this component right here is basically the angle between the two is 90 here. So if we're going to use b cosine 90, of course we get 0 here. So in this case, of course, we're going to get no electromotive force here. So this component induces no electromotive force. This component does, yeah? So this component is basically b cosine theta. That is what we call it, the component of the magnetic field that is perpendicular to the plane of the area. Okay, when we say perpendicular to the plane of the area, that is perpendicular to the surface of the area or parallel to the direction of the area, if we want to put it that way. Okay, so remember this is b cosine theta. Okay, and then we have one more thing. The angle theta is measured between the applied magnetic field and the normal to the plane of the loop here, as indicated in this figure right here. And of course, we have just mentioned that one here. Okay, now let's talk about ways of, or you can say what exactly the magnetic field strength equals to here, because so far we've been talking about that magnetic field strength B equals to or it can be equivalent to so many other units here. Okay, we're going to talk about this one a little bit more here, but in order to do this, by the way, we can manipulate or rearrange these in so many different ways, but of course, perhaps I'm not going to cover every single one of them here. Perhaps I'll do some and then leave the rest for you guys. Now, let's start with chapter 5, or what we have learned. We can say the first thing that we have done, or we went through, it was magnetic flux. We said magnetic flux is basically equals to AB cosine theta, correct? So if we take out B, or if we make this one the subject, B, magnetic field strength, you can say equals to what? Equals to flux or magnetic flux over the area cosine theta here. So if I extract the units of this one here, so B, or magnetic field strength, is basically measured in Tesla, equals to magnetic flux, that is Weber, and of course area is measured in meter squared here. So this is one of the first units that we can have for the magnetic field strength here. That is one. What about the second one here? And then remember, the equation that we've studied after this, of course, it was for, let's say, a charge moving into a magnetic field, let's say, yeah? And of course, we said it will experience a force. That magnetic force was equal to QVB, yes? Okay. And of course, if we make this be the subject here, B equals to magnetic force on that charge, of course, over what? Over QV here. So in this case here, we can say this B is measured in Tesla equals to Newton over what? Over charge is measured in Coulomb, and then velocity measured in meter per second here. Now this one, of course, we can rearrange this one in so many different ways here, because let's say we can bring this second right here, and then what will it become? Okay. So let's see if we can, no, all right. So watch this one here. So this Tesla equals to, we can, by the way, take this second up, or we can bring it right here. Let's not take it to the top first, yeah? So we can say Newton over Coulomb per second multiplied by meter. But you do know that Coulomb per second, that comes from the equation of current here. Current equal to charge over time, yeah? Charge over time is basically what current is. So this is measured in Coulomb, this is measured in second, or Coulomb second, we can say ampere as well. So instead of this one here, we can write Tesla equals to Newton ampere meter here. That is one, yeah? What if I want to take this one to the top in here? It becomes Newton second divided by Coulomb meter as well. Or, by the way, 1 over second, do you know 1 over second, what is it equal to? Isn't it equal to hertz? Yes, so we can say, another unit for this one, of course, we can say equals to Newton. That is basically Coulomb, hertz, and of course meter as well. You see, so you can rearrange these, let's say, of course, units in so many different ways so that you can get different things as well. So far, that is only 2, yes? Okay, now, what equation did we went through after, or did we go through after these, yeah? That is going to be the third one. Let me erase this one here. Let's use a bigger one. Okay, so I think I'll have to remove a lot. Okay, or erase a lot here. So that was the second one, yeah? What about the third one here? The third one, when we had a magnetic force in a wire, let's say, carrying current. So magnetic force was, what was it? Of course, it was BIL, yes? Okay. Once again, if you make B the subject here, that is magnetic field strength equal to what? Equal to magnetic force, and of course divided by current and then multiply by the length as well, yeah? So once again, watch this. That is Tesla, right? Force measured in Newton, current is measured, or current is measured in ampere, and then the length is measured in meter as well. And of course, you saw that we have this just like in the previous equations, of course. Now you can write this one in so many different ways as well, because this ampere obviously equals to Coulomb over second, or you can say charge over second or charge over time, so that is Coulomb over second. The second can go up, and of course you can rearrange in so many different ways as well. That is the third way so far. Yeah. What about the fourth way here? So the fourth way we can say, okay, let's perhaps use this one. These are, by the way, all of them chapter 5, yeah? Now, of course, we can say the fourth way. Now we're dealing with chapter, that was chapter 5. We're dealing with chapter 6 now. So, of course, we can say the electromotive force that is induced is basically equal to what? Equal to negative NAB cosine theta, all right, divided by what? Divided by delta time here. Now, of course, you can make the B the subject here, or you can keep this one and then you can rearrange the equation. It is totally up to you. So let's just, let's say that, let's make B the subject here. So if we make B the subject here, B equals to what? B equals to electromotive force times delta T divided by what? Divided by NA cosine theta. Yeah? Forget the negative here, or we can keep writing it this one as well. So we can say Tesla, remember, magnetic field strength, that is in Tesla. This electromotive force induced, that is in voltage, not Newton, volt, right? This time in second. Of course, you can see here, this number of turns, you can say no unit or just number of turns here. And then cosine theta, we're not taking this one here. So we have area, we can say meter squared for the area. Okay, that is this one as well. And of course, we can add one more as well, yes, because we've learned that using this, or electromotive force equal to the change in the magnetic fields, or the rate of change of magnetic fields here. So we can say voltage equals to negative, or before that, okay, this is basically, let me write it right here. So this is measured in volt, and of course, this is n number of turns. Flux is basically in Weber, and then divided by second as well. So of course, you can see here, this Weber, which we went through, I think previously, equals to what? Equals to volt second as well. This is another important unit that we have. Make sure that you go through all this. And of course, there are more ways where you can manipulate, rearrange these equations so that you can get different things here. But in questions, you might be given a unit, let's say you've never seen before. How do you know if something, let's say, or a unit of something is correct or not? Now, whenever you're given something like this, let's say Tesla or whatever, yeah, they tell you what is exactly, or which one of these units is correct for something. Always, instead of like you can work backward. What do I mean by working backward? Let's say you have these units here. Let's say I've given this unit. Let's say I don't know whether this unit is correct or not. But what I have given here, I do know that Tesla is basically for the magnetic field strength here. And of course, I do have, let's say, the volt. The volt is basically for the electromotive force that is induced here. I do have second. Second is for time, or you can say delta time generally, yeah? And then I have meter squared, and of course, meter squared is for area here. So here's what I need to do normally, yeah? So, of course, now I'll rearrange this equation to see if it makes any sense here, yeah? So, of course, now I can do this one here. Let's say rearrange this one. I can say electromotive force times delta T equals to BA, yeah? And of course, now it kind of like sounds of seeing this equation, or we have something like this. So now, of course, I can move this one right here. So I'll get this one, electromotive force equal to, let's say, A times B, and then divided by delta T. And then, of course, I can add cosine theta if needed as well. So, of course, I do have this equation. So, of course, this equation is one of the units, let's say, for the magnetic field strength as well. So, of course, if it is given as an option, that is one of the correct options that you can have. Okay, so we have a few exotic questions here. It says the equation electromotive force equal to negative n delta AB cosine theta divided by delta T is correctly describes what? Which one of these laws, yeah? Or the law of induction. Is it Ampere's, Faraday's, Hooke's law, or Oersted law? Of course it is Faraday's law. You can see that all of these are very, very interesting. So try to do them all, yeah? Let me do 5 as well. It says the unit of magnetic flux, yeah? Is equal to which one of these, yeah? Let's say this is one of the things that I don't know which one is equal to. So let's say for this one here, magnetic flux, we do know that it is measured in Weber, so I expect you to know this one here. What about in Tesla here? Tesla is basically the unit for magnetic field, yeah? What about volt second? Volt, you see, this is the kind of question that I was telling you about, yeah? So I don't know if it is true, if it is equal to volt second or not, but I'm going to do this one here. So I can say, because it says flux, yeah? So this is basically flux. Volt second, that is basically electromotive force, and then divided by delta T right here. So now, if I rearrange this one here, so electromotive force would be basically, that is basically the subject we normally go through. So equals to, let's say, magnetic flux over delta T, yeah? And what else am I missing here? Of course, you can say this could be one of the correct equations here that we have, because normally we have negative n delta flux over delta Ts, so we don't have any unit for n, you can say, or just number of turns here. So of course this one, you've seen this one before, changing the magnetic flux over the time. Perhaps this is not very clear enough, or we can say electromotive force equal to n, a change in the magnetic flux. Let me not write the n first. We can say change in the magnetic flux over delta Ts. So now we can, of course, add, let's say, an n and a negative 1 here. This two would not, in terms of the units, would not change anything here. But we do have this equation. So, of course, this is also correct for magnetic flux. So, of course, now we can say it is A and C. Okay, and of course, the rest is on you. Okay, now take a look at this one here. It says, what force factor affects the magnitude of the induced electromotive force in a coil? Before you answer these questions, always write the equation, yeah? The main equation. Once you write the main equation, then of course, the rest is going to be very easy. We've learned that electromotive force, right, using Faraday's, electromotive force equals to what? Equals to negative n AB cosine theta, and of course divide by delta time. So can we say, does it depend on the number of turns? Yes. What about the cross-sectional area? Yes. What about B cosine theta? What is B cosine theta? That is the component of the magnetic field that is perpendicular to the plane of the area. Very good. That is basically 3 so far, yeah? What about delta T as well? That is also correct. So that is going to be a total of 4. So you can say number of turns, the area of the coil, the component of the magnetic field that is perpendicular to the plane or to the area, and then of course the time taken for the change as well. So these are the 4 factors that the magnitude of the induced electromotive force in a coil depends on. Remember, that was for a coil, because later on we will have for a solenoid as well. Okay, so we said there are 4 factors basically that affect the magnitude of the electromotive force that is induced here. So in order to answer this question, how you can increase, or you can say So once again, if you have a fixed magnetic field and a length of wire, how can you increase the induced electromotive force across the ends of the wire? In order to answer this question, of course, write the equation one more time, yes? And of course, the equation was electromotive force equal to negative NAB cosine theta, of course, divided by delta T, yeah? So this magnetic field is fixed because it tells you that a fixed magnetic field, yes? So what are the things that we can do here? There are a few options we can do, yeah? One of them is we can, let's say, turn this wire into a coil, let's say, into number of turns. That is one way we can do that, yes? And then, of course, we can, let's say, increase, let's say, or move the coil back and forth into the magnetic field, let's say, way quicker, because these factors, we can change them, yeah? Okay, and of course, you can change the area of this, but because, let's say, the wire that we have, let's say it is limited, so of course, perhaps we cannot change that one very much, because if you're going to change the area, perhaps you might not be able to increase the number of turns into, let's say big enough, yeah? So of course we're going to change the wire into number of turns, and then of course we can let's say decrease the time. By decreasing the time, we can increase the electromotive force that is induced here as well. So of course we can say, using the wire, I'll make the coil with n turns here, okay? Because once again, that is the equation. This is basically fixed or constant, so we cannot do that, let's say. And of course, we can move perpendicular to that one, so you can say this is fixed here. Now, we're either going to change the area or change the number of turns here, but it would be better or easier to, let's say, change the number of turns because it is more practical here. And then, of course, we can, let's say, decrease the time that we move the coil into or out of the coil. So you can, whatever you do is basically right in front of you, or you can, let's say, do whatever that you're doing based on this equation that you have. So once again, I'll make the coil with n turns, then move the coil back and forth rapidly, which this decreases the time, and if we decrease the time, this will increase the induced electromotive force inside the magnetic field. Okay, now this study tip here, of course, we're going to, I'll tell you this one here, but of course we're going to use this one for the following questions as well. So as long as, okay, let's take a look at this one here. Sometimes it says, watch this one closely. Sometimes it tells you that if the coil or the ring is whatever the conductor that you have, basically, if it is pulled out of the magnetic field or the field is removed, that means the magnetic flux will decrease and become zero. Because there will be questions that tells you, let's say the coil is removed, okay? Or the coil is pulled out of the magnetic field, let's say. If that is the case, so we have a magnetic field, that is, you can say, first magnetic field, but once you pull it out, of course, the magnetic field is going to decrease until it becomes zero. So in another way, we can say the final magnetic flux is going to be zero because there's a change, yeah? And then, or you can say the second magnetic field is going to be zero. And of course, if I add one more thing to this, sometimes R is given, yeah? The resistance is given. Whenever resistance is given, that is basically you're going to find the, and they're asking you for, let's say, to find the induced current, we can always use this equation, yeah? V equal to Ohm's law equal to IR. So whenever R is given, it is more likely you need to use this equation. So current is basically equal to V, or you can say electromotive force divided by the resistance. These are basically, we're going to apply these in the next session, inshallah. Till then, keep practicing, and I'll see you soon. Assalamu alaikum wa rahmatullah.